Hi, and welcome to another Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be looking at graphs, limits, and asymptotes of exponential and log functions. So, we've now covered the basics of exponentials and logs along with their algebra and their modeling purposes. Really, once you've tackled all of that, you've really looked at the pre-calculus of exponentials and logs. What we're going to start to get into in the next few lessons then is some of the basic calculus. And of course, calculus always starts with limits, and limits we want to think of in terms of inputs going in some direction and then outputs going somewhere that we're trying to determine. Alright, so let's, in exercise 1, get some sketches of y equals e to the x, y equals e to the negative x, and y equals ln of x. You should be able to do these without your calculator. Now, what I would suggest doing at this point is pausing the video and trying to sketch these three. Alright, if you don't have any idea, then stay with me, and I'm obviously going to walk you through them all. Alright, pause the video now. Okay, let's begin. Now, the most important thing to realize about e to the x is that since e is a number that's approximately 2.7, that means that it's greater than 1. And because it's greater than 1, e to the x will be an increasing exponential. Right? So we should have a very good sense for what increasing exponential functions look like. We graphed them earlier in the unit. You've graphed them hopefully in both Algebra 1 and Algebra 2. Right? They always look something like this. Alright. So this is generally what y equals e to the x looks like. And, just for clarity's purpose, it does have a y-intercept of 1. Now, y equals e to the negative x, you can think about this graph in a lot of different ways. One way to think about it is that it's going to be the reflection of this graph across the y-axis. You've learned that before. If you negate the input, it reflects across the y-axis. Another really nice way of looking about it is that this is 1 over e to the x, which is the same as 1 over e all raised to the x. And since e is about 3, 1 over e is now a base that is between 0 and 1, so it's a decreasing exponential. It then looks something like this. And again, that point 0, 1. Now, y equals ln of x. By definition, this is the inverse of y equals e to the x, right? So all input-output pairs on this graph are going to get reversed, right? Remember how that works? You add x, it goes into f, it goes to y, y then goes into f inverse, which then goes back to x. That almost looks like a little negative 1. Right, so every point on this graph we can take and we can, if you will, switch the roles of the inputs and the outputs, and we can get the graph of y equals ln of x. One point that you could immediately say is on that graph is the point 0, 1. Alright, another trick that you've probably learned in previous courses is that the inverse graph will always be symmetric with the original across the line y equals x. So if I took this curve and I reflected it across this line, what I would end up with is a graph that looks like that. It makes a lot of sense when you look at these. Think about it. Y equals e to the x has a horizontal asymptote of the x-axis, y equals 0. So does y equals e to the negative x. Y equals ln of x, on the other hand, has a vertical asymptote, right, of x equals 0. Let's take a look at number 2. What we now want to be able to do is use these three graphs to think about some very special limits. We're never going to really think about what the limit of e to the x is as x goes to 5, because e to the x is a continuous function, so where it's heading is where it's ending up, if you know what I mean. Same thing with ln of x, e to the negative x, right? Generally speaking, they're continuous. So, ln of x isn't continuous everywhere, but we would only be thinking about it for x greater than 0. The point is, what we're going to be looking at are sort of the special limits. So let's take a look at exercise number 2, and don't forget that you have those graphs up above. So we want to look at where the outputs to all of these expressions are headed as the inputs head to infinity, 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 negative infinity, etc. You can use those graphs to try to figure out these limits, so I want you to pause the video now, and I want you to think about what the values of those limits are. Some of them will be infinite. Alright, let's take a look. So when we look at the limit of e to the x as x goes to infinity, the idea is if we're on this graph and x is heading this way, where is y headed? In my mind, quite clearly it's headed up towards infinity. On the other hand, if x heads towards negative infinity, right, which is going in this direction, then the y-coordinate is getting smaller and smaller, never going negative, no way that that output can go negative, but it's headed towards 0. This is a very important limit, very important. More important, actually, in my mind than this one. Let's take a look at the limit of e to the negative x as x goes to infinity. Well, now we're on this graph. And what we see is that is decreasing and heading towards 0 again. It's going to be a little bit harder to keep the graphs in the range, but if we look at if we look at e to the negative x as x goes to negative infinity, that means we're going to be on here. It means that this graph is just going to be heading north, so to speak, going up and up and up, and therefore it's headed to infinity. Alright, now let's take a look at the ln graph. The ln is very different because its domain is restricted. Right? Logarithms are always restricted to having a domain with the argument being greater than 0, the thing that's inside of the log, right? So if I have the log of whatever, then the whatever has to be greater than 0. Can't take the log of 0, can't take the log of a negative. So we can't really ask what the limit of ln of x is as x approaches 0. I mean, we can, but it wouldn't exist, because the ln of x doesn't even occur out here. So all we can ask is what the limit of ln of x is as x approaches 0 from the right. Remember that notation? It's been a little while, I know. So if we approach 0 from the right, ln of x is headed towards negative infinity. On the other hand, and this is a little bit trickier, right, as x heads out towards infinity, a lot of students will look at the natural log graph and very understandably say, it must have some kind of horizontal asymptote. But it doesn't, right? Just as the e to the x doesn't have a vertical asymptote, ln of x doesn't have a horizontal asymptote, which implies that it just keeps increasing without bound. Therefore, even though it would take a very long time to get there, the limit of ln of x as x goes to infinity is infinity. Right? You'd have to raise e to the infinite power to get infinity. Alright, those limits are very, very important. Alright, some more important than others, especially the ones involving e to the x and e to the negative x, as we'll see next. So based on those limits, I want you to think about what these might be. Really, really ponder them. Pause the tape, to think about them. Letter B, I think, is particularly challenging to consider. If you need to, take your calculator, maybe explore values of that expression, 2 to the x divided by 3 to the x, and allow x to get very, very large, see where that ratio is headed, and see what you can find out. Try your best to do them without the calculator, but if you need to, use calculator table techniques or graphical techniques to see if you can come up with an answer. Alright, pause the video now. Alright, let's take a look. One thing that's always important to remember when you're talking about a limit is that you always have some kind of an expression, right? And you have a variable that's changing. There's change that's occurring, right? Now, there's part of this expression that are changing, like x, and because x is changing, e to the negative x is changing. But you know what? 3 is not, and neither is 2, right? These are constants, so they're not changing at all. That's important, because fundamentally what we want to ask ourselves first and foremost is what's e to the negative x doing as x goes to infinity? Well, as x goes to infinity, e to the negative x heads towards 0. So this entire ratio heads towards 2 plus 0 divided by 3, so we have a limit of 2/3. A lot of students want to just say the limit's 0. Well, okay, yeah, the limit of e to the negative x is 0. But then where the expression is heading towards is 2 plus a very small number divided by 3. All right, let's skip over letter B just for a second. Let's go to letter C. Right, when x goes to 0 here, again, keep in mind what's changing and what's not. Right? Now, this may have thrown you for a loop. Where exactly is e to the 2x headed as x heads towards 0? Well, that's simple. It's headed towards e to the 0. There's no issue there. E to the x is a continuous function. And of course, where is e to the negative x headed towards as x heads towards 0? E to the 0. Now watch out, folks. Even at a very high level, I've seen very talented students say, 2 times e to the 0 is 1, because anything to the 0 is 1. Always remember your order of operations, right? You got to evaluate that first, then multiply by 2. So anyway, it's simple, right? We get 1 plus 5 in the numerator, that's 6. 3 minus 2 in the denominator, that's 6 divided by 1, or 6. Easy peasy. All right, and that's because in letter C it was all continuity. Now this one really challenges students, because you get 2 to the infinity, which is infinite, divided by 3 to the infinity, which is infinite. And a lot of students want to say, well, that's equal to 1. But not my students, right? If you're watching this, not my students, because we did a day earlier this year called Infinity Makes My Head Hurt. And what we learned was that infinity was what's known as an indeterminate quantity. Well, no, infinity is not an indeterminate quantity, but it leads to indeterminate quantities because infinity can be different sizes. So, I don't know, maybe infinity divided by infinity is 1. Maybe it's infinity. Maybe it's 0. And that's actually the case here. And let me show you why. The way that we can think about this is we can say, well, what would really be nice is for me to be able to think about this as a single exponential function. And I can. Remember this exponent property, right? If I have a fraction, let's say a divided by b, raised to the n, I can evaluate that by saying it's a to the n divided by b to the n. But keep in mind, equations are always two-way streets, so that if I have something like this, I can rewrite it like that. So we're used to thinking about it being applied in this direction, but here I'm applying it in this direction. But now we've got an exponential where the base, right, the base is between 1 and 0. And that means that's a decreasing exponential, and therefore this thing has a limit of 0. Very similar to e to the negative x. You never know what infinity divided by infinity will be. Alright, now some sort of random questions here or there to strengthen some skills. Exercise 4 asks us, where will the function y equals ln of quantity x minus 5 have a vertical asymptote? Explain. Alright, pause the video right now and see if you can come up with the answer, and how would you justify it? How would you explain it to somebody? Alright, so hopefully you all said that it has a vertical asymptote at x equals 5. The easiest way to really justify this is to first and foremost appeal to y equals ln of x. This is a graph or a function that you absolutely need to know. It's one of the most important functions in all of math, so memorize its properties if you want to do anything with math in the future. Right? It's a function that has an x-intercept of 1. It has a vertical asymptote of x equals 0. Right here. Right? So what would you say about y equals ln of x minus 5? Its graph must be a shift 5 right of y equals ln of x. We've all learned our shifting rules. So we can produce a graph of ln of x minus 5. Maybe not the best graph. 1, 2, 3, 4, 5. I teach my students how to shift the axes themselves. And then we just redraw ln of x. In fact, we could even say it's got a x-intercept of 6 now. Alright, another random question. I threw in a lot of sort of random stuff in this lesson because they're skills that you need to have as you head into calculus. And many of these skills we're reinforcing today. So, exercise number 5 asks us to determine all solutions to this really ugly looking equation. What I'd like you to do is I'd like you to spend a little bit of time and try to solve this equation. Remember your major equation solving techniques, using inverses, using the zero product law, and, well, that's about it. I mean, there are other ones, right? But those are the biggies. So pause the video and see if you can find all the solutions. All right. Hopefully you found solutions of 0 and 4. Now, I want you to be very careful when you solve equations. All right? When you have equations set equal to 0, I want you to be biased towards the zero product law, towards factoring. Right? I can factor an e to the x out of this equation and be left with x squared minus 4x equals 0. I can continue to factor and pull out a GCF of x, if I so choose, from this parentheses to get this kind of an expression. I bet many of you in my class can already see where this is going, right? Maybe this would be the derivative of a function. We're looking for horizontal tangent lines and turning points, right? And we have to solve. The beautiful thing now is that we have the zero product law, right? We have the product of three quantities, x, e to the x, and x minus 4 all equal to 0. So one of these three things must be equal to 0. That's the zero product law. Well, one of them's done. All right, we're done here. Obviously, this one's pretty trivial, x equals 4. But this one is more questionable, right? What values of x make e to the x equal to 0? And what I tell my students is, I just want you to say there's no solutions. That's what I want you to say, right? You can't take a positive number like 2.7 whatever and raise it to any real number power and get 0. E to the 0 doesn't work. That's 1. E to any positive integer, that doesn't work. That's a number bigger than e. And e to any negative integer, or doesn't have to be integer, I'm sorry, e to any negative real number is 1 over e to the positive version of that number, which is still positive. So there are no solutions to this, right? The reason that y equals e to the x has a horizontal asymptote of y equals 0 is because of this fact, right? This is what gives us that horizontal asymptote of y equals 0 on y equals e to the x. We can't get past 0. We can't even get to 0. All right? So only two solutions, 0 and 4. All right, let's take a look at the last problem. I absolutely love this problem. It's a variation of a problem I saw in the AP exam years ago. I thought it was really, really neat. Exercise number 6 gives us this, I don't know, mishmash exponential function. One might say it's like a cross between a rational function and an exponential function. And then I just ask you to use your calculator to sketch the function on that window. So why don't you pause the video right now, take whatever time you need, get a nice sketch of it. All right, let's take a look. I'm going to open up my TI-84. All right, go into y equals. Let's clear these guys out. This is from the last lesson if you were with me. I don't know why I don't think to pre-clear them, but that's just my own limitations. Okay, let me put the sucker in. Okay, I've got y equals 8 times, where's that e? E to the x, right, minus 9, divided by 4 times e to the x, plus 3. Let me look at my parentheses, make sure everything's fine. Great. Go into my window. I'm going to go with negative 10 to 10. That's good. That's good. What did I want on my y window? Negative 5 to 5. All right, let's take a look at the graph. Ah, the choppiness. That is cool looking, isn't it? I like that graph. What's really, really neat about it in my mind is that there are two distinctly different horizontal asymptotes. Two distinctly different. With a normal rational function, a polynomial divided by a polynomial, almost always, if you've got a horizontal asymptote, it's exactly the same one as x goes to infinity and as x goes to negative infinity. But in this case, there are clearly two. Well, maybe I shouldn't say clearly. but it certainly appears that there are two horizontal asymptotes. The question is, what are their y values? Now, this would be very easy to explore using the calculator. Very easy to explore. All right. In fact, wait a second. Let's go back to the calculator really quick. Let's take a look at a table of values. No, let's just trace. Oh, let me go back. It's getting worse and worse for me. There we go. Let's trace. What does it appear that our y values are headed towards? Looks like maybe y equals 2. I don't know. Sorry. Much faster when I'm actually on my 2 in one direction. And I've got, that's kind of weird. Looks like maybe negative 3 in the other direction. Alright, let's take a look. How do we get these two limits? Let's look at the limit as x goes to negative infinity of 8e to the x minus 9 all over 4e to the x plus 3. If you were with me earlier this year, you'll remember that the way that we determine horizontal asymptotes is by looking at the long-range behavior of a function, i.e. what it's doing as x heads towards infinity or negative infinity. In this case, we're asking, well, what is the output headed towards when x heads towards negative infinity? Keep in mind what we talked about on the front side of the sheet. This is staying the same. This is staying the same, but these two things are changing. Now remember, e to the x heads towards 0, right? So e to the x heads towards 0 as x heads towards negative infinity. So what we're going to end up getting is 8 times 0 minus 9 divided by 4 times 0 plus 3. That's going to be 0 minus 9 divided by 0 plus 3. And we get that horizontal asymptote of y equals negative 3. Cool. That one was easy. The next one, I think I'm going to have to work a little bit harder. Alright, because this would be weird. In this case, we've got, if we think about the behavior of that 8e to the x and 4e to the x, at this point, right, this thing's going to infinity. E to the x is headed towards infinity as x heads towards infinity. So we're going to have 8 times infinity, which is infinity, minus 9, and that's going to be infinity, right? Take a part away from infinity, or add a part to infinity, what remains is infinite. Nice little quote from a Hindu text. Here we'd have another infinity. The problem is, what is that? Right? But here's where the magic comes in math, right? If you studied the long-run behavior of polynomials last year or this year, what you've learned is that the long-run behavior of a polynomial is always dictated by its largest power. And the reason for that is because the largest power is the dominant term. It grows so much more. And that's exactly the way we can look at this. In the numerator, there's 2 terms. It's a binomial, right, because of the subtraction. But one of those terms, this thing, dominates as x goes to infinity. The 9 really doesn't matter. So this would have exactly the same limit as this. The negative 9 really doesn't matter. Likewise in the denominator. The 4e to the x is the dominant term. But at this point, what we see is that the e to the x's can cancel. We'll have a limit of 8 divided by 4, and that's 2. And that was the other horizontal asymptote we saw. So that's it. It's a neat lesson. I like the work that we do with the exponential and the log functions. They are new, and they're a little bit trickier to think about, especially the log. Don't ever forget how to sketch it. It'll help you a lot. All right. Thank you for joining me again. My name is Kirk Weiler. This has been Math 4 Honors. Until next time, keep thinking, keep solving problems.